The hiring problem is a classic optimal stopping challenge. During World War II, doctors faced an impossible dilemma with medical trials. When should they stop testing new treatments? Stop too soon, and you might miss a better cure. Wait too long, and people die untreated. This real-world problem inspired one of computer science's most fascinating puzzles, the secretary problem. Today, we've swapped medical trials for job interviews, but the core question remains. How do you choose the absolute best candidate when you can't go back? Here are the rules. Candidates arrive one by one in random order. You must decide immediately with no second chances. Once rejected, candidates are gone forever. Only one hire is allowed. Your goal is to select the very best candidate overall. Imagine rejecting Albert Einstein because you hadn't seen enough candidates yet. That's the agony of optimal stopping. Here's the smart strategy. First, note your total number of candidates. Say, n equals 10. Interview the first k candidates. Let's pick k equals 4, but reject them all. This establishes your benchmark. For candidates 5 through 10, hire the first one who beats your benchmark. If none do, you must select the last candidate. If candidate number 6 scores higher than your benchmark, you hire them immediately. This sample then leap approach balances exploration and exploitation. Now, what's the probability of hiring the best candidate? What we call the probability of optimal hire. Before calculating this, let's define key terms from our diagram. K is our sample size, the number of candidates we reject to establish a benchmark. I represents the current candidate position we're considering. The probability of optimal hire, denoted P of OH, is our chance of selecting the absolute best candidate. We calculate this by summing probabilities for positions I starting from k plus 1 to n. Why k plus 1? Because our strategy explicitly rejects all first k candidates, making P of OH 0 for any I less than or equal to k. We break this down for a specific position. I, B sub I, candidate I is the globally best candidate. O sub I, no candidate between k plus 1 and I minus 1 was hired. These events are independent. Whether I is best doesn't affect our earlier hiring decisions. Therefore, probability of optimal hire at I equals probability of B sub I multiplied by probability of O sub I. Now we compute each probability separately. First, probability of B sub. E equals 1 divided by n, by uniform probability since any candidate is equally likely to be best. Second, probability of O sub I equals k minus 1 divided by I minus 1. Why? Given I is best, the best candidate in positions 1 to I minus 1 must be in the first k minus 1 positions. This occurs with probability k minus 1 over I minus 1. Therefore, probability of optimal hire at I equals 1 over n, multiplied by k minus 1 over I minus 1. Our final probability sums this from I equals k plus 1 to n. P of OH equals the sum from I equals k plus 1 to n of 1 over n multiplied by k minus 1 over I minus 1. This formula allows us to find the k that maximizes our success rate. Now that we have our probability formula, let's find the magic k value that maximizes our success rate. Through careful mathematical analysis, we discover the optimal strategy is to reject the first k equals n divided by e candidates, where n is our total number of candidates, and e is Euler's famous number, approximately 2.718. This gives us a remarkable rule of thumb. You should always reject the first 37% of candidates, since 1 divided by e is about 0.37. After this observation phase, You're ready to select the next candidate who beats your benchmark. But why 37%? Here's how the math works. Starting with our probability formula for POH, we can approximate the summation term using natural logarithms when dealing with large N. This allows us to express the probability in terms of the ratio of k to n. By taking the derivative of this probability with respect to Kesi, which tells us how the probability changes as we adjust our observation phase, and then setting this derivative equal to 0 to find the maximum point, we arrive at a beautiful result. The optimal ratio of k to n is exactly 1 over e. This mathematical derivation confirms what makes the hiring problem so fascinating. There's a precise, calculable point where the trade-off between gathering information and making a decision is perfectly balanced. The 37% rule isn't just a guess, it's mathematically proven to give you the highest probability of selecting the best candidate. Practical implications. For 100 candidates, reject first 37, then pick the next best. For 10 candidates, reject first 3 to 4, then choose. The probability of success? Approximately 37%, which might seem low but is remarkably good compared to other strategies. And there you have it, the elegant mathematics behind perfect timing. The hiring problem teaches us a powerful life lesson. Whether you're hiring employees, choosing a life partner, or even picking a parking spot, sometimes the best decisions come from knowing when to stop looking and start choosing. While 37% might seem like a surprisingly small chance, it's actually the mathematically guaranteed best possible outcome when facing uncertainty. This same principle powers algorithms in everything from stock trading to organ donor matching, proving that sometimes the solution to life's toughest choices has been hiding in our math textbooks all along. So the next time you face a difficult decision, remember, gather your information, set your benchmark, and when the time is right, make your move with confidence. After all, when mathematics and real-world wisdom align, that's when true optimization begins.